Hello, my name is Carson Sager, and for my final project presentation, I will be doing signature verification using artificial intelligence. So here's a brief history of signature verification. Handwritten signature verification has been used for centuries as a means of verifying identity and detecting fraud, obviously. The earliest methods of signature verification involved visual inspection by human experts who would compare a signature to a known exemplar to determine whether it was genuine or forged. In the 1960s, automated signature verification systems were developed using statistical and pattern recognition techniques such as dynamic time warping and hidden Markov models. These early methods relied on handcrafted features extracted from signature image, such as stroke width, curvature, and direction, and were limited by the quality and variability of the input data. Dynamic time warping, as in the previous point, will be used for the program that I will be using for signature verification. In the 1990s, machine learning techniques such as artificial neural networks and support vector machines were applied to signature verification, allowing for more accurate and robust classification. These early machine learning methods still relied on handcrafted features, but were able to learn more complex and discriminative representations of the signature data. In the early 2000s, ensemble methods such as random forests and AdaBoost were applied to signature verification, allowing for improved performance by combining multiple weak classifiers. These methods still relied on handcrafted features and were limited by the amount and quality of the training data. That's something that I won't have to deal with my model, considering we'll be using a Siamese neural network as well as a convolutional neural network to work together in order to see whether a signature is fraudulent or non-fraudulent. It wasn't until the advent of deep learning and convolutional neural networks like what we'll be using today in the mid-2010s that significant improvements were made in signature verification accuracy, allowing for more robust and reliable systems. Now we're going to move on to the Siamese neural network. Here's a background of the Siamese neural network. This is architecture used for similarity comparison. It's a type of neural network architecture used for similarity comparison. Redundant. It consists of two identical subnetworks that share the same weights and are trained jointly to compute a similarity score between two input data points. Siamese networks are commonly used in applications such as image matching, face recognition, signature verification, and sentence similarity comparison. So there are many other uses besides just signature verification that Siamese neural networks can use. For example, the image matching, face recognition, that's what's used in security and biometrics within for our Face ID for our Apple products, and it compares one-on-one rather than a full data set. So it allows for more versatility, less data usage, and easier access to be able to recognize whether there is an authentic user using some type of interface or it's a fraud or it's a user that's fraudulent. They take two input data points and compute a similarity score between them. Siamese networks can be trained on pairs of input data points, making them well suited for applications where the task is to compare two data points and determine how similar they are. Obviously, this is still kind of saying the same thing here with the Siamese neural network, trying to understand just those two data points rather than having a full set that you have to scan through and look through. They can be used with a wide range of input data types, including images, text, and audio. So, an example of a Siamese neural network is the SIGVER model that I used for this program and this project specifically. It's a deep learning approach for signature verification based on Siamese neural network architecture. It uses a pre-processing pipeline to normalize and augment the input signature images, including resizing, rotation, and elastic distortion. It actually has a great image pre-processing that allows for more accurate and a better representation of each input image, whether you have a large image, a small image. It does very well in understanding where the focal point of the signature is and how to process that. It basically cuts out the rest of the image and only focuses on the signature, which is ideal in any type of signature authentication. It's trained on a large data set of genuine and forged signature pairs using a contrastive loss function that encourages similar signatures to have a small distance in the LERD embedding space, while dissimilar signatures have a large distance. During inference, the model takes a pair of signature images as input and outputs a Euclidean distance metric indicating the likelihood that the two signatures were produced by the same person. Small Euclidean distance between two signature images indicates that they are more likely to have been produced by the same person, while a large Euclidean distance suggests that they are more likely to be from different people. The SIGVER model achieves state-of-the-art performance on several benchmark signature verification datasets, including CDAR, GPDS 160, and MCYT. The authors also propose a novel approach to online signature verification using a dynamic time warping algorithm to align the temporal dynamics of the input signature with a pre-learned template before feeding it into the SIGVER model. This is where the dynamic time warping algorithm that was used a lot of years ago is actually still being used today, but with more advanced technology, with more advanced programming. It allows for more accurate authentication of signatures. Powerful tool for signature verification in various applications is the SIGVER model, including document authentication, financial transactions, and biometric security. So that biometric security is like what we were talking about with the face identification. Financial transactions ensures that the right people are getting the right money or transacting with the right money. It allows just for more privacy, more security, better transactions in the world itself. So now I will switch over to doing a demo using Google Colab, which is the platform I used in order to do the project. I'm not going to go through the code. I'm just going to go through the basics of how this SIGVER model is implementing signature verification and some pretty cool features that it has in order to do signature verification. So now I'm going to share my screen with this the right screen. Okay, so here is here's my code, obviously. So here's some technical stuff that you need to do. Importing. So here's importing the SIGVER library. Yeah, I'll go through here, loading an example signature. They had some example signatures that came with the program, but I decided to use data from friends, classmates, teammates, so that I could have some pretty unique signatures within the program itself. I didn't get a whole lot. I got about 6 or 7 signatures from people that I know, rather than using the data set that he was given, even though it was trained on thousands of pictures and images within these data sets that it was given. So here's me loading in some signatures. I did that manually. It would have been better with a loop, but I processed all the other signatures with a loop. So if the user wants to add data, you can add data. And would you like to add more data? No, I custom made that just in case I wanted to add more data into the program, which was necessary when comparing it with an input signature. So it goes through here, pre-processes the images. Like I said, it's very efficient, very good image processing. So this is also a custom feature I added, was inputting new signature. So I'm now going to share my screen on my iPad with the start broadcast. 2, 1. So now I am sharing my screen on my iPad, and I'm just going to have my signature. See if that works. All right. So here's my signature. I already have my signature within a data set within the program. So let's say I import this to my Google Drive. Make sure it's in the right folder. Export to AI Final. Sending to my Google Drive. So now I'm sending my signature from my Notability app to Google Drive. It was just an easy way to interface my own signature with Google Colab, since it's a virtual environment. It was kind of hard to do anything with the mouse directly onto the computer. So this is the easiest way to input my signature. So now that we did that, done, as you can see, here, I'll share the screen back again. Okay, now let me share the screen. Project. Okay, so now we're back to the code. And as you can see, input signature has been added to the AI final library. Here's other things I did for debugging, understanding what was going on within the code. And then so as we keep going using this device, loading the model, this is just understanding the size, the reshaping of the image in order to allow the model to interact with it. And here is this is just a test distance. This isn't the distance between the input and my data, but here's where we really test if it's me or not. So see, this is between the input image and the array of data that I had within the program. So it's comparing my input image with every image of a signature that was within the program, which is about 7 or 8 signatures that I collected over here. Like I said, I could have done more, but this is the easiest way, and it's pretty efficient because you don't need a whole lot of signatures in order to compare a signature to a signature, since it is a Siamese neural network. Comparing one-on-one allows you to not have to use layers upon layers of additional data other than what was already input into the model that was transferred from SigVer. So I didn't have to develop the model itself, and then adding layers is just basically adding new data points that of people that I know and putting them onto the server. And then once I input a new image, they can automatically check whether it's a valid or invalid signature. So now it's repeating the processing of the image in order to, I wanted to output the images so that we could compare the old and the new one. So here's the database signature and here's my input signature. Obviously they're very similar, and you can tell that, and the test told me that a signature was found. So that's good. And so that it knows that I'm using it. If another signature was found close to it, then it would have told me that, but it's efficient enough to where it knows each unique signature. Okay, and after the program is over, I delete the input signature within my folder so that I can redo the program with another signature if necessary. And that pretty much wraps up the presentation. I have a few sources that I'd like to share. So here are my sources. Here's the source code, and then just a few places that helped me with the information gathering as I completed the project. Thank you very much, and go Pokes.